Hello, today we're going to start Chapter 9, Sequences, Series, and Probability. And we're going to start first by telling you what a sequence is. We're going to use sequence notation to write the terms of a sequence, use factorial notation, use summation notation to write sums, find the sums of infinite series, and then use sequence and series to model and solve real-life problems. So first of all, what is a sequence? A sequence is a function whose domain is a set of positive integers. And when you look at a sequence, you can tell that it's a sequence because usually you have just a list of numbers. And in order to get that list of numbers, they usually follow some type of pattern. And this is a definition of the pattern. The first one here, I have a sub n is equal to n plus 1. So when I go to solve these, what I have to do is, if I want the first 5 terms, unless it tells me otherwise, I'm going to assume that n starts with 1. So I'm going to say A1, in other words, the first term, is equal to 2 times 1 plus 1. When I do that, I get 3. So the first term of my sequence is 3. I'm going to continue that pattern, substituting in 2, 3, 4. And when I do that, and here's all the work, I get 3, 5, 7, 9, 11. So when I write my final answer, I'm just going to write the sequence by listing out the numbers 3, 5, 7, 9, and 11. So let's go to one that has a little bit of a trick to it. So this one here, I have a sub n is equal to 2 minus 1, negative 1 raised to the n power. So again, to find the first term, I'm going to start with 2 minus negative 1 to the first. Well, negative 1 to the first would be negative 1. 2 minus the negative 1 would be 2 plus 1, and I end up with 3. To find the second term, I'm going to do the same thing. 2 minus negative 1 squared. This time, negative 1 squared is a positive 1. 2 minus 1 would be 1. When I go to find the third term, I'm going to have 2 minus negative 1 raised to the third power. So that negative 1 raised to the third power will still be negative. So it'll be 2 minus negative, which will be plus, so I end up with 3. And I can see that this pattern is going to keep on continuing, where I'm just going to alternate between the numbers of 3 and 1. If it's an even term that I'm on, the answer is going to be 1. If it's an odd term, it's going to be 3. So when I list out my sequence, I'm going to write 3, 1, 3, 1, 3, because it asks for the first 5 terms. Okay, to do the next one, I'm going to start off the same way. I'm going to say, let's start with the first term. So a sub 1 is equal to, and then with 2 plus negative 1 to the first all over 1. So that's 2 plus negative 1, which would be 1. 1 divided by 1 is 1. So I'm going to pause the video and give you a chance to finish filling that one out, and we'll see if we match. So I moved to another page to give myself more room. So when I did this, I ended up with the second term being 3 halves, the first term being 1/3, fourth term. So my first term was 1. Then my second term was 3 halves. Third term was 1/3. Fourth term was 3/4. Fifth term was 1/5. And if I had to ask you to continue on the pattern, you should probably notice that the numerators are fluctuating between 1 and 3, and the denominator is just whatever term you're on. That's what the denominator was. So for example, if I wanted you to find the sixth term without having to actually substitute in that formula, I'm going to continue this pattern, and the next numerator would be 3, and then over 6, and then that would probably be simplified to 1/2. So you can continue those by recognizing a pattern. So finding the nth term of a sequence. So we're going to play, it's kind of like a game, I guess is the best way for me to describe it, is you look at these and you're trying to figure out the pattern. So I'm going 2, 5, 8, 3. So the first thing I look for when I'm looking for in a pattern is I want to see if there's anything I recognize that I might be multiplying by or dividing by or adding. In this case, I can go from 2 to 5, I'm adding 3, to go 5 to 8, I'm adding 3, to go to 8 to 11, I'm adding 3. So the next term I would assume would be 11 plus 3, which would be 14. And that would probably continue 17, 20, 23, and so on and so forth. So those are easy ones. Now let's look for some that might be a little bit more challenging. Again, I'm looking for the apparent pattern for the next term. So I have 1, 5, 9, 13, 17. So here I'm adding 4, adding 4, adding 4. Okay, that one's not too tricky. So the next term would be 21, 25, 29. That's it. Again, I'm at home and it just apparently puts these blue lines in there and I don't know what to do about it. So we're just going to go with it. All right, so here I have 2, negative 9, 28, negative 65, and 126. So when I look at this, I know that I'm not adding something. I can see that very clearly that I'm not adding something. What I do notice is I go from positive, negative, positive, negative, positive. So I know that negative 1 raised to some power is going to have something to do with it. So what I want to do is the first thing I'm going to do is I know I had that negative 1. The first term is positive though. So I can't just put n here, because if I put n there, then it's going to be, the first term would be negative, this even terms would be, and that's not what's going to happen. So I have a choice of either writing n plus 1 or n minus 1, so that it's not the same even or odd term that I happen to be on. So let's say I start with negative 1 to the n plus 1. So then I'm going to look for a pattern between, see if I'm multiplying by anything. Well, 2, I can't multiply anything by 2 to get 9. Can't multiply anything by 9 to get 28. So that's not going to work. So I'm going to look for other patterns. And then sometimes I go to squares. So 1 squared is 1, 2 squared is 4, and then we go 9 squared is 9, or 3 squared is 9, 4 squared is 16. That doesn't seem to be working either. So then I try my cubes. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. And I noticed something. I said the cubes are 1, 8, 27, 64, and then 125. Well, I'm not exactly at those numbers. I'm always one more. So what I'm going to do is I'm going to say I'm going to take negative 1 to the n plus 1 power. I'm going to multiply that by n cubed, and then I'm going to add 1. So that is going to be my pattern for the nth term. So if I want the next term, following the sequence, 126 is positive, so then my next term would have to be negative. This was 5 raised to the third power, so now I'm going to have to do 2 raised to the third power, which is 216. But to follow this pattern, I would add 1 more and get 217. So that would be my apparent next term. Okay, recursive sequences. All these ones back here, like when I looked at these ones when I first started here, if I want like of this sequence, if I want let's say I want the 7th term, and so I want the 7th term, all I have to do is substitute in 7, and I will get the answer for the 7th term. If I want the 125th term, all I would have to do is put in 125. These formulas are called explicit, because you don't need anything else. You just need to know the formula and the number of term that you're on. Sometimes, though, it's more beneficial for us to do what's called a recursive sequence. And with a recursive sequence, you need to know what happened before you can get to the next term. I don't know why I'm having difficulty today. There we go. It says you need to know the first few terms, in other words, to find the next term. So when you look at a recursive sequence, it looks a little bit different. So if I look at a recursive sequence, what I'm going to see is I'm always going to tell you what your first term is. So let's say I say my first term is 4. And then I may say to get to the next term, so I'm going to say n plus 1. To get to the next term, I look at the previous term, which would just be n, and let's say I add 5. So when I want to do the second term, if you want to think about this, to get 2 here, that n plus 1 is technically equal to 2, which means n is equal to 1. So to get the second term, I would take the first term and add 5. Well, my first term was 4 and add 5. And I would get my second term to be 9. So the most famous recursive sequence, in my opinion, my humble opinion, is the Fibonacci sequence. And this is how the Fibonacci sequence is defined. It tells you that your a sub 0 term is 1, your first term is 1, your second term, you add the previous 2. To get your third term, you add the previous 2. So you keep on adding the previous 2. So here I can see that I start with 1 and then 1. Then to get to the second term, I add 1 plus 1, which would be 2. To get to the third term, I add 1, which was the first term, plus 2, which was the second term, and I get, oh, didn't mean to put an equal sign there, I get 3. Then to find the fourth term, I take the third term, which was 3, and I add the term before that, which was 2, and I get 5. So to keep on following this pattern, I'm just going to take 5 plus 3 and get 8, 8 plus 5 and get 13, 13 plus 8 and get 21, 21 plus 13 and get 34, and that's how the Fibonacci sequence would continue. You might recognize a Fibonacci sequence because it kind of makes that conic shell. That's what's going on. Write the first 5 terms of the sequence defined recursively. Again, in order to do a recursive sequence, you must have the first term. If I don't have this first term, I cannot do it. You need to know where I'm beginning, because all I'm doing is I'm looking at the previous term and adding 1. So to get to the second term, I'm going to take my first term, which is 6, add 1, get 7. To get to the third term, I take my second term, which was 7, add 1, and get 8. So when I write this, I'm just going to go 6, 7, 8, 9, 10, dot, 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 and it'll keep on going in that pattern. Okay, factorial notation. You've seen factorial notation before. It's the end with the exclamation point, and how that's defined is 1 times 2 times 3 times 4. That would be for factorial. You just keep on multiplying numbers. Very special, something you need to know is that 0 factorial is defined as 1. So it's okay for me to have a problem that says like 3 over 0 factorial, because that just means 3 over 1, which will be 3. So that's very important that you know 3 factorial. Let's start off by talking about your calculator. Find 6 factorial on your calculator. Here's your calculator. Oh, you weren't supposed to see that yet. We'll pretend like you didn't see that. I'm just going to go to a calculating page. Maybe. So if I want 6 factorial, I type in the 6, and right here, this button here has a factorial. See, I'm going to leave it there, highlight for you for a second. See where it is? I press factorial. I press factorial again, and then I hit enter, and it'll do 6 times 5 times 4 times 3 times 2, and that answer is 720. So we got 720 on the calculator. Now some of these, though, before I jump and pick up my calculator, you can do them without your calculator. And yes, there will be one on the test or the quiz without your calculator. So don't ask. Now I told you. So here's 9 factorial. So I see that I have 7 factorial in the denominator. So that is the highest value I have in the denominator. So when I rewrite this 9 factorial, I'm going to rewrite it as 9 times 8 times 7 factorial. Because 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And this 7 factorial, which I'll put here, is 7 times 6 times 5 times 4 times 3 times 2 times 1. So what I've done is I've just taken 9 times 8 and written it as 7 factorial. And that way, I'm going to write 3 factorial is 3 times 2, then 1. And then I have the 7 factorial. Now I can simplify those 7 factorials. And then I can do some more simplifying, because I'm left with 9 times 8 over 3 times 2. The 2 and the 8 will simplify, and I'm left with 4. The 3 and the 9 will simplify, and I'm left with 3. So my final answer is just going to be 12. So I really didn't need my calculator to do that, because I can simplify it. Let's look at this next one here, where I have 3 factorial times 8 factorial over 4 factorial. I start with the largest one, so I'm starting with 8. The largest one I have in the denominator that I can simplify with is one of these 4 factorials. So I'm going to rewrite 8 factorial as 8 times 7 times 6 times 5, and then I'm going to leave it as 4 factorial. This 3 factorial is smaller than, so I'm kind of pairing up this 8 with this 4. So now I'm going to try and pair up this 3 with this 4. So the 3 is a smaller number, so I'm going to leave it as 3 factorial. And then here's this 4 factorial in the denominator. That's that one here. Then this 4 factorial I'm going to rewrite as 4 times 3 factorial. Now I can see that these 3 factorials will simplify, these 4 factorials will simplify, and this 4 will simplify with the 8, and I'll be left with 2. So now left to do this problem, I'm going to take 2 times 7 times 6 times 5. So that's 10, 42, 420 would be my final answer. And boy, you better check my math. I'm hoping I'm right. All right, I'm going to pause the video and give you a second to try and think about this one before I ruin the surprise. So think about that one for 1 minute. Okay, so we're thinking about this one right here. So what I'm going to do is this n plus 1, I'm following the same pattern as this 9 factorial times 8 factorial. And I'm going to think of this n plus 1 factorial as n plus 1 times 1 less than that, which would be n factorial, all over n factorial. And here I can see that the n factorials will simplify, and I'm left with an answer of n plus 1. Again, I don't know why it's changing colors. All right, write the first 5 terms of the sequence given by the following formula. Begin. This is one where I told you you have to watch, because sometimes they don't want you to start with 1, and they will always tell you if they want you to start with something different than 1. Here they're saying they want you to begin with n is equal to 0. So I can do that. So I'm saying a sub 0 is equal to 3 raised to the 0 power plus 1 over 0 factorial. 3, any number raised to 0 power is 1, so my numerator is going to be 2. 0 factorial, remember, is defined as 1. So that first term is 2. Then when I put in 1, I'm going to have 3 to the first plus 1 over 1 factorial. And I end up with 4 over 1, which will just be 4. Continuing on, it wants the first 5 terms, so I'm going to work on finding the first 5 terms. You work on find the first 5 terms. Okay, so here's what I got when I finished. I have 2, 4, 5, 14 1/3, and then finally ended up with 41 over 12. Then it asked me the graph on the set of coordinate axes, so I put it into my calculator, I put it on the list and spreadsheet, and here's the values that I put, and then here's my graph. So then what I'm going to do is I'm just going to bring that graph, hopefully, on here. Nope, I'm not. That's okay. That's okay, we'll try again. Try again. New, do it again. And we'll bring it up here. And there's my graph. And then based a little later on in the chapter, we're going to figure out how we can take this graph and model it a different way. But we just wanted to kind of look at the shape. And if I ask you to look at the shape, and I ask you what kind of function you think it might resemble, I'm hoping based on the shape of it, you can say it kind of looks somewhat, you can recognize the parent function, I guess is what I'm saying. It kind of looks like it might be parabola, but we'll do that later, not today. So now we're going to talk about summation notation, which is used with the Greek letter sigma. And then what we're going to do here is we are going to take a sequence and we're going to add the first couple terms. The number down here that I see here, this is where I begin. That's my index. And then this upper number tells me how many terms I'm going to add. Usually I list out all the terms that I'm adding. And then let's just do one. So if I have this problem here, it's asking me to start at 1 and go to 5. So I start by putting 1 in for I. So I'm going to say 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. So 3 plus 6 plus 9 plus 12 plus 15. Add those all up and I get a sum of, gosh, I don't know. and I get a sum of 45. Whoopsie, 45. So I'm going ahead and do the next one, and I'll give you a second to do this one and to do this one, and we'll check our answers in a minute. Okay, when you did this one, the summation from 2 to the 5 of 2 plus k to the third, that's down here. The work for that one's down here. You should have had 10 plus 29 plus 66 plus 127. That final answer is 232. The next one I moved to the other page because I needed some space. So here I have the summation from 1 to 6 of 2 over I factorial. So in the red is my work 2 over 1 factorial, 2 over 2 times 1, 2 over 2, 3 plus 2. The 2's simplify every time. So I end up with this 2 plus 1 plus 1/3 plus 1/12 plus 1/6. And my final answer is 1237.60. Now that's a pretty complicated problem. You know, I had to go on my calculator because I didn't want to find the lowest common denominator in order to do that. So you have to be asking yourself, there has to be a better way. And there is a better way, and that's, I'm going to show you how to use your calculator. So you have your calculator. We're going to do the last problem that we just did. We're going to do the summation starting at I is equal to 1 to 6 of 2 over I factorial. So when I pull out my calculator, I'm going to press menu. On the menu, I see a number 4 says calculus, and we'll press calculus. Whoops. So menu, calculus, and then number 3 is sum. At least number 3 in my calculator is sum. You're going to look for summation. And when I click on that, hold on, I don't know what's going on. When I click on that, I should get the summation symbol that I just saw. And now I'm going to fill it in. So right now it's blinking. I'm going to type it in exactly the way I saw it. So I saw it with an I, so I'm going to use I. And then I'm going to hit the right arrow to go over, and I start with I is equal to 1. Hit the right arrow again, maybe, and that puts me in my function box. So I'm going to go ahead and type in my function now, using my favorite button to get that division bar, which I didn't do. Oh, come on. So I'm going to do 2, press the down arrow for I want I, so I have to go back and do I. It really doesn't matter what letter you use as long as these 2 letters match. And then I want factorial, so I'm pressing the button where my factorial is hidden. And I'm going to hit the up arrow key again. Oopsie, I'm not going to do that. And I'm going to get out of there, and now I'm going to hit the up arrow key until I'm on top of my sigma sign, and then I'm going to press the 6. And then we'll press enter. And I forgot to put the factorial sign in. Oh, why didn't you guys tell me that? I'm going to go down here, and I'm just going to edit it. Maybe. Maybe not. Now I'm going to put the factorial sign in here. I thought it was in before. Apparently it didn't go in. There we go. Now I'm going to hit enter. And I got the same answer that I got before. Okay, these are properties of summations. Basically what it's saying is I can separate. So if I have like, this one is saying if I have like a summation of I is equal to 1 to 6, and I'm doing like 3i, what I could do is I could bring that 3 out in front and just do the summation of I. So what I could do is I could add 1 plus 2 plus 3 plus 4 plus 5 plus 6, get that answer, and then multiply it by 3 instead of adding 3 plus 6 plus 9 plus 12 plus 15. This one is saying is if I'm taking the summation of a sum, I can break it up into the 2 partial sums, same with the differences. Oopsie. A definition of a series is when you are doing the sum. So a sequence, you just list the numbers. A series is when you add the numbers. So if I know that I'm going from what we've just been doing, where I have a definite starting point and a definite ending point, that's called a partial sum. Like I'm adding the first 6 terms, the first 3 terms, whatever. If I have an infinite series, I'm going to see a sigma up here, which means that I'm going to keep on adding. And sometimes I can get a definite sum for that, and sometimes I can't. Sometimes I get a close approximation. So if I have this one where I'm taking, for the series, find the first wants me to find the third partial sum of 5 over 10 to the n. So to do part A, I'm doing a partial sum. So I'm going to start with n is equal to 1. I'm going to do 3, and I'm doing 5 over 10 to the third. So when I do that, I'm going to have 5 over 1,000 plus, oh, nope, I did that wrong. Ugh. That's my third term. So sorry. So let me go backwards. I'm going to erase that, pretend like that never happened. So when I go to find the first term, I'm going to have 5 over 10 to the first plus 5 over 10 squared plus 5 over 10 to the third. When I do that, I'm going to have 5 tenths, which would be 0.5, plus 5 hundredths, which would be 0.05, plus 5 thousandths, which would be 0.005. When I add these, I'm going to end up with 0.555. So when I go to do the second part, which is asking me to find the sum, in other words, the entire sum up to infinity, I realize that I see a certain pattern here. It's 0.5, then 0.05, then 0.005, and it's going to keep on continuing to add a 0 each time. So it's going to end up being 0.55555, or 0.5 repeating, which as a fraction I can write as 5/9. So what I'd like you to do is, this is your homework on page 649, do these problems. If you have any questions, just hold them for class on next time I see you, and I hope this video helped.